เดือดร้อนคุณจังเลยเนี่ย
ไม่ต้องไปใช้ภาพจากกล้องหรือภาพจากนาซาที่เราจะดึงจากไลท์ยูมานาซามันไลท์อยู่ก็ทุกวันนี้ก็มีนาซาเยอะ
เงียบเย็นเนาะ
นาซายังนอกโลกไลท์อยู่แล้วนี่ออกนิ้ว
ลิงก์ไงวะลิงก์
เรียกเบราว์เซอร์ผ่านเลยที่เรียกเอาไว้เท่านั้นเลยพี่
เคียงใช่ปะ
ใช่
ผมไม่ใส่แว่นไม่ใส่
พวกเอ็นดำนะโอ้โห
กดไม่โดน
หลับดีวะเอาเสียงมาด้วยเลยขวาที่ขวาเมาส์
It's been very quiet, very difficult to launch.
Do you think we're going to launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the Aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to get.
My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth, 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachutes help us hit the brakes, but not too quickly. One day people will be aboard, so deceleration must happen in stages to keep things comfortable for the crew. The forward bay cover jettisons. Two drogue chutes deploy and slow the returning spacecraft down to 175 miles per hour. Then, the three main parachutes open. Once fully engaged, this canopy would cover an American football field. It takes parachutes this size and strength to slow our descent to 20 miles per hour, and then splashdown. For this first flight, we won't have astronauts inside, but we still have some very precious cargo. The flight data from this mission is stored inside the Orion spacecraft. While our flight might be over, there is still a lot of work to do. Onboard sensors recorded every detail, from launch to flying in space, to re-entry to landing. Flight tests are difficult and complex, but they give us confidence that the systems we have designed work under real flight conditions. It's great to be a part of this first space flight for Orion, and we're looking forward to beginning a new chapter in human space exploration.
Welcome to NASA Edge, an inside and outside look at all things NASA. We're joined by Michelle Monk and Steve Gaddis. How you guys doing?
Great.
And we have a very important topic today, and that's going to be EDL, or Entry, Descent, and Landing. Now, Michelle, you're the principal technologist for EDL.
Yes.
What is Entry, Descent, and Landing?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to a planetary surface. So the entry part refers to, the atmospheric flight, most of it, and then we have descent and landing, which is usually propulsive and get us down on the surface safely. We do D and L at places that don't have atmospheres like the moon or, asteroids, but usually we talk about EDL when we talk about atmospheres.
So Michelle, what is your role as principal technologist for EDL?
I look across all the missions that NASA has coming up that will use entry, descent, and landing on any planet, and I look at the technologies we're going to need for those missions, and I bring them forward to the mission directorate for starting funding. So you have a need in the EDL world, in the community. You're coming up with the technologies that are needed for future missions. Right. So you take some of those technologies that maybe are less mature, hand them off to you. Right. And then you mature those technologies.
Design, develop, test, and evaluate.
Is that a pretty easy task, trying to figure out
Not at all.
what technology you're going to need?
Not at all. I have to look at both the human missions that are coming up, so, sending humans to Mars. Right. I have to look at the scientific missions that are coming up and all the destinations the scientists want to go to. And I have to kind of rank those and prioritize them and figure out, where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have to figure out what is the best program within STMD for the figure out, where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have to figure out what is the best program within STMD for the investment. Is it better to have a university work on it, or a small business, or is it better for a game-changing program element?
And your job is really hard, because we're going to be talking about a suite of EDL projects over the next 2 shows, because there's so much content in EDL. We can't do this into one show.
Absolutely.
So this will be part 1 of 2 parts. So how do you manage all that?
Well, one is it's hard, but it's also fun. Okay. And we've got excellent technologists leading every one of these activities, so we all work together. And we all know that we need these technologies, so we're motivated to see them be successful.
We're a very passionate community.
Yes.
I've seen it in all the interviews that we've done. You guys are definitely passionate. Now, the first one that we're going to be talking about is ESM, or Entry Systems Modeling. What is that about?
So that's the first part of it, where they develop these models and simulations to understand how the technology works and how it will be beneficial at a system level. It's very cross-cutting against all the projects, and the plan is to take that data and then infuse it into the projects.
Blair had a chance to go out to NASA Ames Research Center to talk to Mike Barnhart, who is the Integrated EDL Systems Lead. Let's check it out.
Mike, tell me a little bit about Entry Systems Modeling Project. What is it?
So the Entry Systems Modeling Project is tasked with developing a lot of these technologies that are coming from lower technology readiness level, things like academia, and trying to bring them up to a level so that we're ready to help them.
So in this particular situation, we're talking about EDL projects, and so you're actually helping them raise their technology readiness level?
That's right. So any of these things, Orion, Mars 2020, Mars InSight, anybody that's flying anywhere in the solar system and they need to enter an atmosphere, you have to go through an entry, descent, and landing phase. And we don't have all those problems solved. We don't have all those technologies built. And so we're continually trying to improve on our existing technologies and also renew with new ideas. And that's the real purpose of the Entry Systems Modeling Project.
How do we get the data we need to improve the EDL process across these missions?
Right, so there's a lot of different things that we can do. We have ground facilities, which we rely on a lot. So we have arc jets that we do for material characterization and developing models for material response. We have our shock tubes, which we use to develop radiation models. We have wind tunnels that we use to build aerodynamic models. the dynamic motion of a body as it's flying, that sort of thing. We need to know all that in order to have a successful entry into a planetary atmosphere. So that's the simplest thing that we have access to every day. And then we also have, you know, some amount of flight data. So there was the Orion EFT-1 flight last year, which was very successful, and we can use that to take our models and look at our predictions and then try and back out, you know, exactly how well are we doing, quantify, you know, how well are we predicting that.
You used a lot of data from the Apollo era. Are you able to use data from things like MSL and more recent missions to help? Because I know we have limited data on entry.
Yeah, so, you know, MSL is a really great example because we flew Medley on MSL, and that allowed us to get some of the only data that we've had on entry at Mars. So heating data, pressure data, which we use to reconstruct the aerodynamics, is a fantastic tool for us, but there's a lot of challenges there as well. So it's really, you know, it takes a village. You need to have your computational models because they're the only thing that's going to access the true flight space that we have here on the ground. We have ground facilities that simulate parts of the flight space, and then ultimately you have a little bit of flight data. And your goal is ground to flight traceability. Let's predict what we do on the ground. Let's predict what we do in the air. And let's see, you know, how far apart are we so that we can quantify when we're designing the next mission exactly where we think we'll be.
Are you sharing that data with all the different EDL potential systems that are being developed?
Absolutely, absolutely. Everything that we do in the InterSystems Modeling Project is, you know, for the greater good. We work very closely with academia. So we've got university partners that we are sharing this data with to help improve our models. We share it with other projects. So with radiation modeling, we were working very closely with the InSight project and OSIRIS-REx projects because they had issues with radiative heating on their back shell. So they call us because we're the radiation modeling experts, and they say, here's our problem, tell us, you know, how worried do we need to be?
Be worried, be very worried.
Yeah, we're always looking to help everyone else around the agency, and that's really what Space Technology Mission Director is all about, right? Is trying to help the other directorates with the technology that they're going to need.
Tell you what, great interview with Mike Barnhart. I mean, it really kind of gives you the flavor of how difficult EDL really is.
Right.
I mean, if you can't characterize it and model it here on the ground,
Yeah.
I mean, you'll never be able to land.
That's right.
And you can't test an entry system on the ground and get the flight-like data that you need to design.
And that's the challenge but with Medley on MSL, that was a game changer, wasn't it?
Absolutely.
I mean, you actually, for the first time, were able to actually see the health of the spacecraft as it was entering the atmosphere.
Yeah.
Right. As engineers, you know, it's great that we succeeded, but I want to know if I got an A+ or a C- on the design. So the Medley data allowed us to actually know how we designed the vehicle.
And based on that Medley data, what were the results? They were pretty good, weren't they?
They were fantastic. But we found some things that we didn't know. Radiative heating is important at Mars and at the scale of MSL. We didn't recognize that before.
And now, since it was such an important mission for you guys, now you're going to take it to the next level for Medley 2 for Mars 2020.
For Mars 2020, yeah, we've got that going, and they're right in the middle of their preliminary design phase.
Right.
They're all excited. They're going to put some new measurements on the back shell.
Yeah, they were actually at Aberdeen Proving Ground last week doing some testing to see where to put the pressure measurement on the back of the vehicle.
Right.
So yeah, it's really exciting to get this new data in the back shell and using new sensors.
We know Blair had a chance to sit down with Mark Schonenberger, who's the reconstructionally, which I got to ask you about that when we come back, because I never heard of a reconstructionally, but we're going to learn more about Medley 2. Let's check it out.
So Mark, when we think about the differences between Medley 1 and Medley 2, it's interesting because Medley 1, the M stood for MSL, Mars Science Laboratory. Now it's Mars 2020. You guys caught a break. You get to use the same letter.
We still get to use the same letter. I think it'll just be shortened to Mars, EDL instrumentation, and it'll hopefully continue for a bunch more Medleys, Medley 3, 4. We can always call it Mars.
Perfect. It's a nice little series you got going.
We're getting great data. So.
Now I'm wondering though, in terms of technology and in terms of how you're growing Medley, I mean, Medley 1 was a very successful mission as far as the data we got back. What are we expecting for Medley 2?
For Medley 2, it's really to dig in and look at the pieces that we couldn't quite get for Medley 1. The instrumentation there was to really, it was the first time we'd flown instrumentation since Viking to get pressure and heating data. So we really tried to capture the whole event. And to do that, especially for pressures, we had these transducers that could see the peak high pressure as you went through the hypersonic phase, and you're really slowing down around Mach 18. And then as you slow down, you really start getting in the noise there with the kind of information you can get. The signal was just really weak. It's sort of like using your bathroom scale to measure the ingredients for a cake. It's just, you know, there's not a lot of resolution there. So it's tough. You don't really trust those measurements.
That's about how my cakes turn out,
that's
if
right.
I measured ingredients with the...
So what we did here now is to use more of a postal scale for pressure. So we're measuring down at the low range when we're flying supersonically. Right as we get near parachute deploy, we're spending a lot of time just kind of slowing down, flying at the same altitude. But you're really at terminal velocity. You're not slowing down real well.
Now, is that pretty much in the part of the descent, if you will, that where you've burned away most of the heat shield that you're going to in the process?
Yeah, all the heating's over. I mean, it's still a little warm and things are kind of winding down. But yeah, all the exciting heating stuff is over. And you're really just trying to bleed off energy until you get down to a condition that's safe for the parachute. And so any error in your prediction of how that vehicle slows down, or your prediction of what the atmosphere is going to end up being on the day at Mars, can lead to being far uprange or far downrange. You know, your landing ellipse and how you target it, you need to account for that. So if we can get better data to characterize the aerodynamics, we can tighten that up and land in even smaller spaces.
Which is always the goal, right?
Yep.
You're trying to find out exactly where you need to land.
Yep.
So Mark, how is the instrumentation different on Medley 2 from Medley 1?
So, at least from where my experiences with the pressure side, Medley 1 was really designed to capture the pressure all the way through entry. So it had this nice high maximum pressure it could measure. What we really wanted to do for Medley 2 was to look for the low pressures right before chute deploy. We're going to be coasting there, slowing down from, say, Mach 4 down to Mach 2 for a minute, 100 seconds, something like that. And that adds to the landing ellipse, any error in aerodynamics. So the transducers, we put more of them on the heat shield, and they're at a lower range, so they'll have much better resolution at those low speeds. So we can pull out things like winds, and we can get a better estimate of the drag. And we also have a pressure transducer on the backside. As you slow down, get down to supersonic speeds, the pressures on the back shell become a big contributor to the total forces acting on the capsule. And it's really hard to predict, actually, what those pressures are. So with some truth on the backside, that can really help us nail down the total behavior of the capsule as it's flying at those low speeds.
It seems like we're getting an awful lot of good data on the things that are happening during EDL and Mars, especially for Medley and Medley 2. Are we able to, in the future, maybe translate what you're doing here to potential different atmospheres or different EDL circumstances?
Absolutely. So Medley 1 definitely demonstrated, and it was the reason I think we have Medley 2, was it became the model of how you put an instrument package on a heat shield, how to work with the project to do it, so that they're not scared about putting holes in their pristine heat shield that's designed to get their rover on the ground. We have a process now to do that. So you'll see missions going to Venus or Jupiter, Titan, those kinds of things. They'll all have instrumentation during entry, and NASA has the confidence to require that because we did so well with Medley 1 and hopefully again with Medley 2.
Mark did a really nice job discussing Medley 2, but I have to ask the question, in all my years at NASA, talking to subject matter experts from all 10 centers, what is a reconstruction lead?
Reconstruction is really important after a flight to understand exactly how and where the vehicle flew.
Oh, okay.
And without the proper data, it's really hard. You have to make some assumptions.
Okay.
So for instance, before Medley, when we didn't have an independent pressure measurement, we had to assume something about the aerodynamics of the vehicle in order to figure out how it flew.
Okay.
Now with that independent pressure measurement, we can nail it and we don't have to make any assumptions. So reconstruction lead is really key to understanding how we did.
See, you learn something new every day. I had no clue.
Yeah, he comes back up with that flight plan that they had, and where the data is along those flight plans. You know, it's very important.
Now, speaking of that flight plan, with Medley 2, can you take the data from Medley 1 and kind of show what the flight plan is going to be for Mars 2020, or is that a completely different flight plan?
It's a lot the same because it's the same shape, size, vehicle. The mass will probably be a little different. They're using the same entry, descent, and landing system, but the atmosphere obviously will be a little bit different. The entry velocity will be a little bit different because of the different year.
Right.
But largely, you know, we're going to use all of our MSL simulations as the basis for where we start on 2020.
Now, I know, Steve, with game changing, you take technologies and you take them from a technology readiness level. We always talked about that 1 through that 9 scale.
Yeah.
And you're in that middle range.
Middle range, about 3 to 5 or 6.
Right. So, but with Medley, since you have proven you have a flight underneath you, and then you're working on Medley 2, is that still considered, you know,
Yes.
technology at that level?
Yeah,
It's still not space ready.
Yeah, and it was like what Michelle was telling you was we learned so much through Medley 1 that we want to put different kinds of transducers to get the lower pressure range. We want to understand the back shell pressures and radiation rates. So we learned so much, so it's not really just a repeat of Medley 1.
Yeah, we have totally new sensors. Knowing what we know from Medley 1, we've moved a lot of our sensors, so we have kind of the same number of channels of data, but we've distributed them differently on the forebody and then moved some to the back of the vehicle.
Well, speaking of a new mission, we also have now, instead of Medley 2, we also have HIAD 2.
Yep.
Absolutely.
Which is a hypersonic aerodynamic inflatable decelerator.
Inflatable aerodynamic, yes.
Oh, we did it again. It's a hypersonic inflatable aerodynamic decelerator?
Yes.
Bravo.
Very cool.
Bravo.
All right, so that's a completely different type of EDL system from Medley 2.
It is.
And Franklin had a chance to sit down with the project manager, Joe Del Corso.
Yes.
And we're going to learn more about HIAD 2, so let's check that out.
So Joe, we're talking about HIAD 2. Tell me what has changed since HIAD 1.
So we've had a number of changes. The first one was we upgraded our thermal protection system. In HIAD 1, we used a Generation 1 thermal protection system, which was somewhat capable. It's low temperature capable, basically something on the order of 1,000 to 1,100 degrees Celsius on the surface. For HIAD 2, what we've looked at is much higher temperature capable materials, much more flexible and lighter weight. So now we're using custom built silicon carbide materials as an outer fabric. We're using COTS materials and some custom materials for our insulator systems. And then on the backside for the gas barrier, you have woven fabric systems with PTFE film wrapped around it. Our inflatable structure is also being upgraded. And then the other thing that we're doing is we are working on scalability. We're focusing on trying to get to a 12-meter scale. In order to do that, we've got to upgrade a lot of our equipment. We've got to work on something as simple as just picking up one of the gore seams. It takes a lot of development, a lot of careful coordination. So what we're focused on is not just upgrading our materials, but also upgrading our handling techniques, our manufacturing techniques.
Tell me about the HIAD timeline from the time it was conceived to where we are right now with HIAD 2.
So HIAD has been in development, previously it wasn't known as HIAD, but it's been in development now for almost a decade, and we still have probably another 4 years worth of work to do to get us to human access to Mars. We started out in 2006 doing material testing, and really all we were doing is we were doing low-level, trying to learn how to test fabric systems so that we could simulate an atmospheric entry condition. We were learning how to learn in the early phases. We had IRVI-1 happen. Unfortunately, there was a launch vehicle anomaly, so we lost that. But what it did do is enabled us to put in place IRVI-2 flight tests. People had enough confidence in what we were doing that they allowed us to build a build-to-print. That went up on a sounding rocket, launched out of Wallops, and it was an incredibly successful proof of concept. We had an inflatable structure, but no real TPS at the time, thermal protection system. Following the success of IRVI-2, we started up what we currently know as HIAD, which is the Hypersonic Inflatable Aerodynamic Decelerator project. During that project, we were doing all the lab scale development, small scale, little samples. We had learned how to do the initial testing. Now we were taking it through a maturation process, getting it ready for flight again. The third flight that we flew out of Wallops again was called Irby 3. That was a much higher heating condition, and it was the first chance for us to actually test a thermal protection system with our inflatable structure. After the success of Irby 3 and the closure of the initial HIAD, we attempted to fly an orbital entry flight test called THOR, the Terrestrial HIAD Orbital Reentry Flight Test. Unfortunately, due to the ORB-3 failure, we had to cancel THOR and we went back to a ground development effort. But unlike the first two ground development efforts, the third one wasn't focused on learning how to test or testing materials or developing materials. It's focused on scaling. So we did small scale in the early development phases, and now we're scaling to something more applicable for human access to Mars.
Now, the cool thing I understand about HIAD 2, that you guys have a partnership with ULA?
Yeah.
Let's talk about that.
So about a year ago, ULA announced that they wanted to use HIAD technology to recover their boosters as part of their new business model, affordability. And so we've been working on a flight demonstration with them over the last year and a half.
Yeah, and that would be at the 6 meter scale, which is about halfway to what ULA would need for their full booster recovery, 12 meters that Joe talked about on the video. And it's also the right scale for us to do maybe a technology demonstration mission leading up to putting humans on Mars.
So the idea is that you're using this HIAD technology to recover the first stage of a ULA rocket. And so is that going to be recoverable, and is that going to sort of land in the ocean? Is it going to land on dry land? How is that going to work?
They actually want to snatch it out of midair with a helicopter and to minimize any refurbishment costs.
Wait a minute, so you're going to have this...
Catherine, question for you. Short question. So what vehicle are going to fly? The Soyuz or the Dragon? I'm very happy to fly on the Soyuz. It's a very, very reliable vehicle. But of course, I hope we'll be able to see the Dragon on board the station. It's a very beautiful sight. Thank you. Thanks.
У вас была дополнительная возможность, дополнительный канал связи. Вам придется уметь делать. Платка находится в специальном аппарате, стёгнутый, распаковываете.
Now, second fit check.
Спасибо. Вам спасибо. Спасибо. Именно эти НИПы позволяют выдавать силовые скорости разворотов. Нагорный тренинг. Принял? 5 метров. Разложение. Движение звонил. Да. Опа. О. Не попробуешь. Пара ударов.
Let's count. 1, 2, 3, 4, 5, 6, 7, 8.
Куда? Прошу обратить внимание. Все? Нет. Кейт?
Да.
Oleg Urusov, the town's administration. Catherine, question for you. Can you tell us whether the medical experiments on board the station are going to help us to fight COVID-19 and other diseases? We don't really study viruses because the station is a pressurized volume. It's contained. We can examine how the virus inside the body acts. And that's something we do. And we do study the shingles virus. That's true. Thank you.
Спасибо.
Thanks.
Кэтлин, а у вас
Кэтлин,
какая любимая
what's your
жанровая
favorite music?
музыка по жанрам?
Maybe a surprise for you. Hope you like it. Thank you.
Спасибо большое. Спасибо.
Kate, I have two questions for you. The first one, you are arriving on station at an extremely busy time of visiting vehicles, crew rotations, and a ramp-up of scientific activities. How do you plan to balance out all that work, coupled with the orientation of the new crew members who will be arriving a couple weeks later on the next SpaceX Crew Dragon vehicle?
Good question, John. Thanks.
Most of our ops on board are managed by the ops plan team on the ground, so they will take care of all of the balancing of activities. In this case, we're very lucky that 3 of the 4 new crew members arriving already have space station experience, so I expect that we'll get to work right away.
Thank you. Second question, as we approach the 20th anniversary of a permanent human presence on board ISS, it is sometimes overlooked as to how remarkable the technical stamina of the station is, both in its daily performance and the relative absence of technical problems. What are your thoughts on how well the ISS has stood the test of time?
ISS is an incredible machine. It's a technological and engineering testament to what humanity can do when we build something together. It's incredibly impressive to see in space, but I'm also not surprised that it's still flying 20 years later. The incredible workmanship and the engineering that has gone into this is hopefully going to allow us to fly this station for many years to come.
The Soyuz is ready.
Спасибо. На меня.
Только надо ли? Вот, спасибо.
Кузьмин Дмитрий, позвоните 7357.
еще можно как-то правду? Станция, он как бы жаль, корабль заряжена. Вот это будет видно. Вот так вот она находится.
Так, ребят.
Can you print out extra? And I'll wear 2 brains.
Для всех.
It actually fits.
Закрыть регулятор на нижнюю.
Catherine, question for you. Short question. So what vehicle going to fly? The Soyuz or the Dragon? I'm very happy to fly on the Soyuz. It's a very, very reliable vehicle. But of course, I hope we'll be able to see the Dragon on board the station. It's a very beautiful sight. Thank you. Thanks.
Аппарат. У вас была дополнительная возможность, дополнительный канал связи. Вам придется делать платка находится в специальном аппарате, стёгнутый, распаковываете.
Мы встречаемся с вами.
Now, second fit check.
Договорились. Спасибо.
Вам спасибо большое. Спасибо. Именно эти нипы позволяют выдавать силовые скорости вооружения. Принял? 5 метров. Движение замер. Да. Опа. О. Не попробуешь. Пара ударов.
Оп. Это, в общем,
Let's count. 1, 2, 3, 4, 5, 6, 7, 7, 8.
Куда? Прошу обратить внимание. Все? Нет. Ты?
Да.
Oleg Urusov, the town's administration. Catherine, question for you. Can you tell us whether the medical experiments on board the station are going to help us to fight COVID-19 and other diseases? We don't really study viruses because the station is a pressurized volume. It's contained. We can examine how the virus inside the body acts. And that's something we do. And we do study the shingles virus. That's true. Thank you.
Спасибо.
Thanks.
У вас
Catherine,
какая любимая
what's your
жанровая
favorite music?
музыка по жанрам?
Maybe a surprise for you. Hope you like it. Thank
Спасибо
you.
большое. Спасибо.
Kate, I have two questions for you. The first one, you are arriving on station at an extremely busy time of visiting vehicles, crew rotations, and a ramp-up of scientific activities. How do you plan to balance out all that work, coupled with the orientation of the new crew members who will be arriving a couple weeks later on the next SpaceX Crew Dragon vehicle?
Good question, John. Thanks.
Most of our ops on board are managed by the ops plan team on the ground, so they will take care of all of the balancing of activities. In this case, we're very lucky that 3 of the 4 new crew members arriving already have space station experience, so I expect that we'll get to work right away.
Thank you. Second question, as we approach the 20th anniversary of a permanent human presence on board ISS, it is sometimes overlooked as to how remarkable the technical stamina of the station is, both in its daily performance and the relative absence of technical problems. What are your thoughts on how well the ISS has stood the test of time?
ISS is an incredible machine. It's a technological and engineering testament to what humanity can do when we build something together. It's incredibly impressive to see in space, but I'm also not surprised that it's still flying 20 years later. The incredible workmanship and the engineering that has gone into this is hopefully going to allow us to fly this station for many years to come.
Добрый день.
Спасибо. Все, спасибо вам большое.
Хорошо.
Ага. Я здесь.
Ага, вот.
Марк.
Сергей.
Сергей.
Сергей. Ребят, на нас.
9.
Там и там язык у нас. Все. Все.
Осмотр, гуляем. Господи.
Еще здесь все специалисты здесь. Через неделю.
Здравствуйте. Очень рада вас приветствовать в нашем музее. Проходите, пожалуйста.
Маня?
Ладно. Улыбка.
Еще раз.
Истории.
Ничего не...
Ну, следующий.
Ну.
Это ваш предыдущий полет?
Не, я понял.
Да. Распишитесь где-нибудь, чтобы это, понимаете, для архива, для музея.
Просто подпись?
Да.
Все, спасибо.
Station, this is Houston. Are you ready for the event?
Hello, Houston. This is the station. Ready for the event.
Time 100 talks. This is Mission Control Houston. Please call station for a voice check.
Station, this is Time. How do you hear me?
Hello, Time. Welcome aboard the International Space Station. I hear you loud and clear. Great to be with you today.
Thank you so much for having us. It's great to be here. And Chris, I just want to get right into some of our questions. This is your third time in space, your third rotation through the ISS. That's time enough for space to maybe have lost a little of its novelty, for it to feel a little bit more like a job. But do you ever get past what astronauts call the overview effect, that sense of looking down at the Earth and seeing its wonderful beauty and destructibility?
Well, that's is certainly an effect that we have. I'll tell you though that it does, like with any job, I'm sure it does sometimes feel like a job. The difference is you have to you check yourself periodically as you float by the window and see the beautiful planet below you that you described. And I'm sure sports figures, when they walk out onto the field, sometimes forget that, think of it as a job and forget about how lucky they are to be playing at that level. And it's the same for us. This morning I was knee-deep in bags unloading a cargo ship, and I was passed by the cupola window and did exactly that, realized how lucky am I to be orbiting our planet and have this amazing view right now. Pretty special.
Special indeed. The space station has now been continually occupied for 20 years or a bit more. And yet, strangely, if you ask the American public, a lot of people aren't aware of that very fact, and they're also not aware of some of the good science, the great science that's come out of the ISS. What do you think is responsible for that public disconnect?
Yeah, that's an interesting thing to think about, and I would argue that there's probably not a lot of public knowledge about laboratories on Earth that are producing great science as well. So scientific output is unfortunately just not on the forefront of people's minds as they go about their daily life and doing their job or their school or whatever the people are doing. And when there's a breakthrough in technology, a breakthrough in scientific knowledge, that gets attention, and at a world-class laboratory on Earth, just like it would up here. And then flying in space for 20 years, maybe it's come to seem routine, and then it's not risky. Well, I'll tell you, space flight is challenging. Every day we're here is a difficult day to manage, both for the ground and the crew. And but maybe that's a good thing that we have got to the point where we've got our hands around that difficulty, and we're able to make it where it does seem like spaceflight is routine, just like flying an aircraft from New York to LA, for example.
Sure, and in some ways that's a good thing if people begin to accept it as simply a routine part of life. In another direction, back in the 60s, the space program commanded about 4% of the national budget, which is a considerable amount of money. Now it's about 0.4%, and there doesn't seem to be a whole lot of public support for spending yet more on space. Why do you think that? Has America fallen out of love with the fascination and the thrill of space travel?
You know, one of the cool things about being an astronaut is we get to travel around the country when we're not in space, and it's not 2020, and talk about space and share thoughts with folks. And my personal observation is people have not lost interest in space exploration, both manned and unmanned. Space captures people's attention and imagination and excitement. What I think that the challenge, though, is back then in the 60s we were in a race, and again, people relate to things that people can relate to on their own personal life. And imagine you're running a road race and you're in a competition head to head with a few other runners, and you've got 3 or 4 laps to go around the track. You can put more effort on the table if you know that you're trying to beat a person or two. If you're just going out and jogging and there's not necessarily a race and you're just doing your daily exercise, you might not need to put forth so much effort. And in this case, my analogy, effort equates to the percentage of the budget and how much we're willing to throw in there. So I think that the space race that we had going on at the time was a huge part that allowed the nation's appetite to swallow the higher percentage of the budget.
Right, understood. One of the most exciting developments of the last few years is the Artemis program, the commitment to have American astronauts back on the moon by 2024. But that mission, the landing mission, is supposed to happen after just a single circumlunar mission with astronauts aboard. Now, back in the Apollo era, we had Apollos 7, 8, 9, and 10 that tested the command module and the lunar module in Earth orbit and in lunar orbit. Do you think it's a safe model this time to scrap all of those incremental steps and have one circumlunar flight and then go straight on the stick the landing flight?
Well, you bring up a good point. There's certainly more buy down in your risk. You have higher safety margins if you fly more test flights. More test flights equates to more dollars. So program managers, of which I'm not one, but program managers have really tough decisions to make, where you're weighing budget versus risk and timeline, and you've got a couple big knobs to turn, and they all impact each other. So would it be safer to fly more test flights? Absolutely, no question. There's no way anyone can argue that. The question then becomes, how few test flights can you accept and have risk that's tolerable? The one difference that comes to mind also is we as a nation have, and as a globe, have much more spaceflight experience under our belts now in 2020 than we did in late 1960s. So I think that goes a little bit into the equation as well. We fully understand, or we understand the technical side of it. Certainly there's unknown unknowns with any endeavor, but so I think the decades of experience combined with just tough decisions on how to manage time, budget, and technical risk.
Right. Back then we were learning how to do it for the first time, and now we sort of know how to do it. There's that institutional memory. Shifting gears slightly to geopolitics, our biggest competitor in space right now is not the old Soviet Union, it's China. Would you be in favor of the U.S. collaborating with China and perhaps even collaborating within the partnership of the International Space Station? Do you think we're ready for that kind of work together?
Well, I can only answer your question from the crew perspective. I think if our nations got together and decided collectively to work in space together, I would open my arms wide open and say, come on in, taikonauts, let's go. Let's talk about how you execute your procedures, how we execute our procedures. This is how we do a burn, deorbit burn, for example. This is how we operate on the space station. I would think it would be super cool. One of the most memorable things for me about flying on board the International Space Station is the international cultural aspect of it on a person-to-person basis with my crewmates. Having other food, having other music, having other just political discussions, life discussions around the dinner table makes the 6 months just super memorable. Yeah, all the science we do and spacewalks we do and robotic operations are fantastic, and I love every minute of those. But in the end, when I'm an old guy and telling stories to my grandchildren, it'll probably be about the friendships I've made on the space station, and I think it would be cool to add one more country to that list.
Well, and we certainly saw that back when there were tensions between the U.S. and Russia with Ukraine and Crimea, and yet the astronauts aboard the ISS simply transcended that. They were all just crewmates working together. Geopolitics meant nothing.
Agree.
Some of the most thrilling work that's been carried out in space has been carried out by uncrewed, unmanned spacecraft. They're cheaper, they don't risk human life, and there is a school of thought that this is really the way to go. What do you say to folks who say, let's stop risking people and do all of our deep space missions robotically? How do you answer that argument?
Well, I think if you do 100% missions robotically, you're going to miss a key aspect, and that is how manned missions bring it up close and personal, and you really get a sense for living the mission through the astronaut's eyes, if you will. People can relate to people. It's difficult to relate to a robot driving around. You can, and it's exciting to think about a Mars rover and look at the camera views, and the new Mars rover will even have audio, and to hear sounds of the tires crushing gravel is super, super cool. But then to put on top of that a person's feelings. How did you feel when your feet were crushing the gravel and you bent over and you picked up that rock and you looked out and you saw the horizon on the moon or the Mars curvature of the surface? How did that make you feel? And though that's a key part, now how do you put a scientific value or worth on feelings? And that's kind of touchy-feely, and it doesn't really have a place in a line item on a budget. But I think that robotic and human manned missions are dovetailed in their success of one another. We need the robotic missions to have safe human missions, and it just works together. I think they go hand in hand.
I think you're absolutely right that there is no way to have a line item in a budget for human inspiration. There's just no way of putting a price tag on that. One other direction I wanted to go. Space tourism certainly is, a very big market right now, or there certainly is talk of developing a very big market in space tourism. And while it's wonderful to think of space hotels and even suborbital flights, the physics of space travel don't change. It is still pretty punishing to tolerate the speeds and the G-forces of going up and coming down. Do you think that average people who may have the money for a space tourism experience can withstand the kind of G-forces and physics that you folks, trained astronauts, have spent hours and hours and hours in centrifuges and planes trying to acclimate yourself to?
Well, I mean, is there some portion of the population out there that it's not suited for? Yeah, absolutely. But I do think that as sometime in the future, and who knows how many years or decades in the away that is, it will be something that people can throw a credit card down and buy a ticket, and maybe you just have a small checkout that you have to do, kind of like if you're going to go be a scuba diver. You can do a couple of lessons in your local swimming pool with your dive master and get a card, and now you're certified to go off and dive in the ocean or wherever you want to take it. And so there's probably some type of regulation that goes into it. I'm sure we wouldn't want to just completely open it to anybody, because as you correctly identify, you are subjecting your body to the G-forces going up and the G-forces coming back, and those are not insignificant. But it's something that is very doable. We're just normal people. We happen to be doing this as a profession, but our bodies are no different than anyone else's, and the only difference is we get seen and get a healthy upcheck from our flight surgeons before we strap onto the rocket, and I foresee that some kind of hybrid thing like that being the case.
We hear a lot of talk these days about the financial possibilities in lunar mining, but getting material to and from the lunar surface can be awfully expensive. I mean, just putting a pound of payload into low Earth orbit can cost $10,000. Do you think lunar mining will ever be realistic, or that future moon bases will instead be more like Antarctic bases, just fixed research institutions in a very rugged environment?
Yeah, this is a little bit beyond my subject matter expertise, but my personal feeling is that it'll be very difficult to ever completely sever the umbilical cord from Earth to a lunar outpost. Do I think that lunar mining is realistic? Yeah. Do I think that it'll supply every single bit of consumables that people or a group of people need? Probably not. So they'll need some sort of logistics and resupply, and the more we can fine-tune our ability to use the in situ resources on the lunar surface, of course, the better off we are, because it brings down the cost of the mission. But it's definitely a challenging proposition.
Now, NASA is very committed not just to returning astronauts to the moon, but to the Moon to Mars program. As far back as 1969, after Apollo 11 landed, a crewed landing on Mars was considered about 15 years in the future. And at any given point since then, Mars has always been 15 years in the future. That's where we are right now. The best bet is that sometime in the mid-2030s, we'll be able to have astronauts on Mars. What do you think about that? When do you think we will actually see boots on the red planet?
Well, I'm going to be a little bit creative and say it's not 15 years away. It's 20. No, I'm kind of being facetious in there and a little bit of a joke, but it's hard, it's difficult, and it all boils down. Again, this is just my personal opinion about life, but anything technical is solvable, and that the time scale in which you solve that is just about resources and how much. We have a ton of smart people in the world, and if you put all those smart people and unlimited resources on it, we could be on the moon faster than 15 years. Now, there's still some technologies out there that'll help us greatly, and that's different types of propulsion systems that can get us there quicker and that sort of thing, and figuring out the landing and the habitat. So there's stuff that has to be built, and building stuff takes time. So there's a certain number of years that once you say, ready, set, go, here's a pile of resources, here's a pile of people, it's still going to take like a decade, I think, from that point. And so it boils down to resources and money and funding and will. But I think that's why you have this kind of constant 15-year sliding scale, because if today they said, ready, set, go, 15 years is a nice, reasonable number that you can make it happen. So given the fact that coronavirus has just kind of turned our world upside down and our financial markets upside down, I'm going to say we just bought 20 years instead of 15.
And one final quick question. The Cygnus cargo vehicle that just arrived at the station is carrying a 3D virtual reality camera that will help humans on Earth experience a spacewalk in VR. Now, there are only a couple of hundred people who have ever had that transcendent experience of walking in space. What do you think the value is of allowing people on Earth to see what you folks see when you are actually outside your spacecraft?
Well, I think that people need to know that spacewalks are hard. And spacewalks are my favorite thing to do. I love them, but it's a challenging day. It's a hard day for the crew, for the technicians, for the engineers, and it's difficult. Even with the most intricate camera system that you have, we had the luxury of some HD little mini cameras out there with us this last spacewalk, Bob and I, and those are fantastic images. But what they don't convey, and it's really, really hard to convey, is the blackness of space, the brightness of Earth, the contrast between the two. What does it look like to see 250 miles below you, passing by at 5 miles a second? And oh, by the way, the shiny metal thing that you have in your hand that has serial number 0001, there's only one of them. Don't screw that thing up, because if you screw it up, that whole part of the expedition is ruined. So it's hard to lump all that up into a snowball and throw it in someone's face, but I'm excited for cool cameras to try.
That sounds fantastic. I want to thank you so much for the time you've given us today. I know your schedule is impossibly busy, and safe travels. Come home to us soon. We look forward to welcoming you back on Earth.
Thanks so much. I really enjoyed your thought-provoking questions. Have a great day.
You too.
Station, this is Houston ACR. That concludes our event as we count down to 20 continuous years of humans living and working on the International Space Station.
Thank you to all participants from Time 100 Talks Station. We are now resuming operational audio communications.
The Soyuz is ready.
основных групп дизайн.
Спасибо. На меня.
Только надо ли? Вот, спасибо.
Кузьмин Дмитрий, позвоните, 7357.
Там еще можно как-то правду? А станцию он как бы жаль, корабль заряжена. Вот это будет видно. Вот так вот она находится.
Так, ребят.
Can you come help make sure and I'll wear 2 braids.
Для всех.
It actually fits.
Catherine, question for you. Short question. So what vehicle going to fly? The Soyuz or the Dragon? I'm very happy to fly on the Soyuz. It's a very, very reliable vehicle. But of course, I hope we'll be able to see the Dragon on board the station. It's a very beautiful sight. Thank you. Thanks.
Аппарат. У вас была дополнительная возможность, дополнительный канал связи. Вам придется делать платка находится в специальном аппарате, пристегнутый к распаковываете.
Мы встречаемся с вами.
Now a second fit check.
Договорились. Спасибо.
Вам спасибо.
Спасибо.
Именно эти НИПы позволяют выдавать силовые скорости такого рода. Принял? 5 метров. Да. Опа. О. Не попробуешь. Пару ударов.
Let's count. 1, 2, 3, 4, 5, 6, 7, 8.
Куда? Прошу обратить внимание.
Все?
Нет.
Кейт.
Да.
Oleg Urusov, the town's administration. Catherine, question for you. Can you tell us whether the medical experiments on board the station are going to help us to fight COVID-19 and other diseases? We don't really study viruses because the station is a pressurized volume. It's contained. We can examine how the virus inside the body acts. And that's something we do. And we do study the shingles virus. That's true. Thank you.
Спасибо.
Thanks.
У вас
Kathleen,
какая любимая
what's your
жанровая
favorite music?
музыка по жанрам?
Maybe a surprise for you. Hope you like it. Thank
Спасибо
you.
большое. Спасибо.
Kate, I have two questions for you. The first one, you are arriving on station at an extremely busy time of visiting vehicles, crew rotations, and a ramp-up of scientific activities. How do you plan to balance out all that work, coupled with the orientation of the new crew members who will be arriving a couple weeks later on the next SpaceX Crew Dragon vehicle?
Good question, John. Thanks.
Most of our ops on board are managed by the ops plan team on the ground, so they will take care of all of the balancing of activities. In this case, we're very lucky that 3 of the 4 new crew members arriving already have space station experience, so I expect that we'll get to work right away.
Thank you. Second question, as we approach the 20th anniversary of a permanent human presence on board ISS, it is sometimes overlooked as to how remarkable the technical stamina of the station is, both in its daily performance and the relative absence of technical problems. What are your thoughts on how well the ISS has stood the test of time?
ISS is an incredible machine. It's a technological and engineering testament to what humanity can do when we build something together. It's incredibly impressive to see in space, but I'm also not surprised that it's still flying 20 years later. The incredible workmanship and the engineering that has gone into this is hopefully going to allow us to fly this station for many years to come.
Добрый день.
Спасибо. Все, спасибо вам большое.
Хорошо.
Ага. Я здесь. Ага, вот. Марк.
Сергей.
Вперед.
Ребят, на нас.
Где?
Там и там обязательно
Все. Осмотр, гуляем. Господи. Еще здесь все специалисты здесь. Через неделю.
Здравствуйте. Очень рада вас приветствовать в нашем музее. Проходите, пожалуйста.
Маня.
Ладно. Улыбка.
Еще раз.
Истории.
Ничего не... Ну да, они родили.
Ну, следующий.
Ну.
Это ваш предыдущий полет?
Не, я
Посмотрите,
понял.
да. Распишитесь где-нибудь, чтобы это, понимаете, это для архива, для музея.
Просто подпись?
Да.
Все, спасибо.
The Soyuz is ready.
За основным группочерки заняты.
Спасибо. На меня. Только надо ли? Вот, спасибо.
Кузьмин Дмитрий, позвоните, 73-57.
Там еще можно как-то правду? Станция, он как бы жарко, наряжена. Как это будет видно? Просто вот так вот она находится.
Так, это передать?
And I'll wear 2 braids.
Для всех.
It actually fits.
Закрыть регулятор на нижнем уровне.
Catherine, question for you. Short question. So what vehicle going to fly? The Soyuz or the Dragon? I'm very happy to fly on the Soyuz. It's a very, very reliable vehicle. But of course, I hope we'll be able to see the Dragon on board the station. It's a very beautiful sight. Thank you. Thanks.
У вас была дополнительная возможность, дополнительный канал связи. Вам придется иметь дело, платка находится в специальном аппарате, пристегнутый, распаковываете.
Мы встречаемся с вами.
Now, second fit check.
Договорились. Спасибо.
Вам спасибо.
Спасибо.
Именно эти НИПы позволяют выдавать силовые скорости разного рода. Народный тренинг. Чтобы у вас потребность принял. 5 метров. Разложение. Жирный момент. Да. Опа. О. Не попробуешь. Майя ударил.
Let's count. 1, 2, 3, 4, 5, 6, 7, 8.
Куда?
Прошу обратить внимание.
Все?
Нет.
Ты?
Oleg Urusov, the town's administration. Catherine, question for you. Can you tell us whether the medical experiments on board the station are going to help us to fight COVID-19 and other diseases? We don't really study viruses because the station is a pressurized volume. It's contained. We can